Hello, Chem 2, and welcome to part 2 of Chapter 1. We're going to look at Section 2, which is going to revolve around a lot about measurements, significant figures, and calculations. It's going to be a kind of a long one. It's a lot of videos here, but we're going to go ahead and dive right into it. So first off, let me get rid of my face. Homework for your stuff. You're going to finally get a chance to start diving into the idea of the owl. In class, I'll share with you a little bit about how to do the owl, how to incorporate the owl, how to use the owl. There should already be on your Google Classroom in the resources a registration for the owl. And again, I'll share, give a little bit more about that in our synchronous time. So let's get to it. So Chapter 1, Matter and Measurements. We're going to do Section 2, which is all about measurements. And we're going to start by looking at all this stuff. This is all about conversions and sig figs and conversions between units and blah, blah, blah. That's all going to be involved in this section. We're not going to do the last two. That's going to be in the next section. The last two are density and how they relate and solubility. But as a warm-up, a student needed a cube of metal which had to have a mass of 80 grams. He knew the density of the metal was 8.67 grams per mil, because he knew what the metal was, which told him the cube's volume. Well, it could if you did your math right. Question to you is, what is the length of one side of the cube? Now, this is going to be a cube, so the volume of a cube is width times height times depth, but all three are going to be the same. So it's going to be whatever the length is of a side, cubed is going to be the volume. So pause the video right now and try this one on your own. I'm going to throw down the gauntlet. I bet you no one can figure this one out. Maybe I'm right. Maybe I'm wrong. Give it a look. That's my phone ringing. Okay, so did you get... I'm not going to tell you. It was that kind of a lead-in. You'll get to it later. We're going to talk about it in a second, how they would do this. But it's a lead-in to why we need significant figures and why we need to use the idea of significant figures. So here's a story. A student once needed a cube of metal which had to have a mass of 80 grams. He knew the density of the metal was 8.67 grams per mil, just like the warm-up, which told him the cube's volume. Believing significant figures were just invented to make his life difficult for chemistry students and had no practical purpose in the real world, he calculated the volume of the cube to be, did you get 9.227 milliliters? Okay. He then determined that the edge had to be 2.097 centimeters, because a milliliter is a centimeter cubed. A milliliter is 1 centimeter cubed. He took his plans to the machine shop where his friend had done the same work the previous year because he had the same project. And the shop foreman told me, yeah, we can do that according to your specifications, but it's going to be expensive. He didn't think anything more of it because it's important. He knew his friend paid a whopping $35 a year before, and he was allowed to have $50 towards the school's budget to get it done. So he returned the next day, expecting the job to be done. Sorry, said the foreman. We're still working on it. Try next week. Finally, the day came, and our friend got his cube. He looked very, very smooth and shiny and beautiful in his nice velvet case. And seeing that our hero had a premonition of disaster, became a bit nervous. He summed up enough courage to ask for the bill, and he said $500, and it's cheap for that price. You're getting a bargain. We had a terrific job getting it right. Had to make 3 before we got it, get that one exactly right. But my friend paid only $35 last year. He says, no. Your friend asked for a cube that was 2.1 centimeters on an edge. You asked specifically for a 2.097 because that's what your calculator gave you. So yours roughed out to that 2.1 that afternoon, no problem. Could have zipped that, boom, been done in maybe an hour. But it was precision grinding and lapping to get it down to exactly what you wanted, the 2.097, which took so long and cost the big money. The first one we made was 2.089 on an edge, and that was way off. That was, 8 1/1000ths of a centimeter off. So we had to scrap it. And the second was closer. Was not what you specified. That's why it took 3 tries. And all our friend had to say was, oh. This is to indicate maybe sometimes you don't just trust your calculator and just use the numbers that come right off the calculator. The numbers that he came up with, the 2.097 centimeters, was what the calculator spit out when he did the math. However, really, since this only had, remember Chem 1 guys, sig figs, this only had 2 sig figs, you only have to do your final result of your calculated value to 2 sig figs. He could have just said that 2.01 centimeters on edge. Anyway, let's talk about measurements. Measurements. We're going to use length, width, and length, weights, and volume. Length, we're going to use the meter as our standard unit, but we're more often going to look at centimeters because that's a more reasonable size for us. But a centimeter is 1/100th of a meter. A millimeter is 1,000th of a millimeter. We might use kilo, we might use nano, but we're going to look at the unit of measurement of being meters. And you usually measure it with a ruler or a caliper or something. Volume, it's a unit, it's a cubic, it's a derived unit. It's actually a cubic length. Length times width times height, like you did with the cube. You have 1 cubic centimeter is equal to 1/100th of a meter cubed, or 10 to the negative 6 meters cubed. Really, really small part. So there's a million millimeters in a meter cubed. We also may see the liter. The liter by definition is a decimeter cubed. Very, very decimeter by a decimeter by a decimeter. And sometimes we're going to use, more often than not, we're going to talk about the milliliter because it's a reasonable size. And that is the size of a centimeter cubed. A centimeter on each side would be equal to a milliliter. We're going to use graduated cylinders if we ever get to class, or pipettes or burettes. We're going to use all these different things whenever we get to class. What about those units? Well, we're going to use grams or kilograms, more often grams. And for weight and mass are not the same. You remember that from physics. Weight is a gravitational force that acts on the object, and mass is the actual inertia that the object has. So, base units. For mass, in physics, you dealt with the kilogram. Now, I will say the SI unit is kilogram for all of your calculations and such, but we're going to be using the gram more than anything else. Length, it's the meter. Time, second. Temperature, the Kelvin. Do you remember the Kelvin from Chem 1? And then the amount is the mole. The end of Chem 1, you were introduced to the concept of the mole. And that's where you measure the counting number, how many of things there are. Prefixes, you should memorize, or you should already know these. These are from middle school. Kilo is 1,000. Hecto is 100. Deca is 10. Deci is 1/10. Centi is 1/100th. And milli is 1,000th. So if I had to convert between kilometers, to meters, what I would do is say that there are 3.59 kilometers, and I would use what's called dimensional analysis, make my units cancel. Now, the way I express it is if I look at kilo, we look in the previous slide, I'm going to go back to it, kilo is 10 to the third. So kilo means 10 to the third. So I'm going to put meters on top and meters on top and meters on bottom. And then, since I want to cancel the K, I put the K on the bottom, and I put the number equivalent on the opposite side of the measurement. So now kilometers cancel, and I get 3.59 times 10 to the third meters, or 3590 meters. Okay. Now, what about these ones where they go from centi to hecto? So it goes from 2 separate prefixes. Well, if I go back to my previous slide again, I see a centi is 10 to the negative 2. So centi is 10 to the negative 2. And I go back to the previous slide, I see the hecto is 10 to the second. Hecto is 10 to the second. Well, I'm going to do the same logic of this dimensional analysis. 6.575 centigrams. Now, I got to put grams on both sides. But since I want to cancel that C, I'm going to put the C on the bottom, and then I'm going to put the number equivalent up top, 10 to the negative second. Then that gets me the grams because my centigrams cancel. Well, I want to get to hecto. So I want hecto to be on top, or hecta. So I'm going to put hectograms on top, but it's opposite of the H. I'm I'm going to put the 10 to the second. And if I do that math, I get that I have 6.575 times 10 to negative fourth hectograms. Okay, so that's dimensional analysis, where you cancel out the units to make sure you go from whatever unit you're starting with to the unit you are seeking. Now, here are some less common prefixes, but some of them are moderately common. Since we have computer technologies, you've become much, much more aware of the megas, the gigas, and the teras because of the speed of your computers, or maybe the capacity of the memory in your computers or your phones. You're familiar with mega, giga, and tera. Mega is a million, giga is a billion, and tera is a trillion, or 10 to the 6th, 10 to the 9th, and 10 to the 12th. On the other side, you're probably not as familiar with those, but they're prefixes nonetheless. Micro is 10 to the negative 6, so that's 1 millionth. Nano is 10 to the negative 9th, that's 1 billionth. Pico is 10 to the negative 12th, that's 1 trillionth. And femto, almost never used, but it's kind of cute to say, is 10 to the negative 15th. So these are prefixes that are used reasonably common, especially these ones in the middle, talking about really, really big numbers and really, really small numbers. And you should memorize these. These are ones that maybe you weren't introduced to in middle school, and maybe not even in Chem 1. I know if you had me, this was introduced to you. So let's talk about this one. What if I go from gigaliters to milliliters? Well, this is the same idea as before. I'm going to start with 1.535 times 10 to the negative 10th gigaliters. I want to cancel. We just said giga. See, giga was 10 to the what? Let's go back. Giga was 10 to the 9th. So giga was 10 to the 9th. And let's see, milli. Milli, that was on the other slide. Milli was 10 to the negative 3rd. Milli, 10 to the negative 3rd. Okay, so let's see. Giga to liters. So I'm going to put a giga on the bottom. Liters. Opposite my G, I'm going to put the 10 to the 9th. And then for the second one, I'm going to put liters on the bottom and my milliliters on top. And opposite my milli, 10 to the negative 3rd. So when I do this, I get that answer to be 1.535 times 10 to the second milliliters, or 3.5 milliliters. Okay, so just conversions, simple conversions, at the beginning of the use of dimensional analysis. And I would suggest that for all problems, you get in the habit of using and showing your work using dimensional analysis. Okay, next thing to worry about as far as measurements is temperature. There's three measurements of temperature. There's the Celsius scale, the Fahrenheit scale, and the Kelvin scale. And on one of the problems on the diagnostic, they had you kind of convert between the three. So how would you do that? Well, first off, the conversion that is present to go from Celsius to Fahrenheit is a little complicated. Okay, Celsius to Fahrenheit is really, really complicated because you've got some weird conversions in there, 9/5 or 5/9. And no matter what do you do with the 32, do you add it or you subtract it? But if I want to get my number in Fahrenheit, okay, I'm going to take whatever my Celsius temperature is first, multiply it times 9/5. Do that first. Then whatever number I get from that, I'm going to add 32 to. And we're going to treat that as an exact number for sig figs. We'll talk about sig figs in a second. Okay? For Celsius, you're going to take your Fahrenheit number and you're first going to subtract the 32, and then you're going to multiply it times 5/9. So you want to do the 32, negative 32 first for going from Fahrenheit to Celsius. Okay? Kelvin's pretty easy. Kelvin is a straight conversion. Kelvin and the Celsius scale have the same size units of measurement. It's just the numbers are all much bigger on the Kelvin scale. On the Kelvin scale, you're going to take whatever the Celsius value is and just add 273.15. And the story behind that is Lord Kelvin wanted a temperature scale that gave only positive numbers. So he tried to figure out what was the lowest possible number? What was the lowest possible temperature that could be um, achieved? So he did some tests and extrapolated, which means expanded his knowledge to a point. He says, well, the lowest possible temperature that I'm going to see on a Celsius scale is going to be negative. Why can I do this? It's going to be negative 273.15 degrees Celsius. It's the lowest I'm going to see. So what he did was he said, well, I'm going to just call that 0. And he called it 0 kelvins because he was Lord Kelvin and named it after himself. So he made it 0. And that means all he did for the scale was move everything down 273.15 units. So if you were to go from Celsius to Kelvin, you add 273.15. If you go from Kelvin to Celsius, you subtract 273.15. So let's check this out. What is the Fahrenheit temperature that is equivalent to 18.72 degrees Celsius? Well, remember, in order to get Fahrenheit, what you're going to do is take 9/5 times the Celsius temperature and then add 32. So we're going to take 9/5 times 18.72 and then add 32. And I'm going to take my handy dandy calculator out and figure that out. Okay, so let's see. 18.72 times 9 divided by 5. And if I add 32 to that, the number that I get is, let's see, the sig fig should be 4 sig figs. It's going to be 65.70. And that's degrees Fahrenheit. Okay? Kind of chilly. Not too bad, but kind of chilly. Okay, so what's that temperature going to be in kelvins? So in kelvins, we know that kelvins are simply Celsius plus 273.15. So we're going to take the Celsius number, 18.72, and add to it 273.15. And let's see if we can do that on a calculator. So I got 7, 8, 11, 9, 291.7, and it's kelvins. It's not degrees kelvins, it's just kelvins. Hope I did that right. It'd be kind of foolish if I didn't. Okay, so that's your conversions between temperature. Now let's get to the crux of this, the hard part of this. Significant figures and significant digits. In the anticipatory set, the beginning part of this, we talked about the fact that that person incorrectly gave a very, very small measurement, a very, very precise measurement, when really he didn't have to, because he didn't have to have like 80.0000 grams. He just wanted 80, plus or minus 1. So the significant figures are a way of determining or showing how confident or how precise your unit of measurement is. So for instance, if I put a weight on a balance and it were to say 12 grams, in a calculator, if I put it on another balance, it might say 12.0000 grams. Well, in the calculator, that's the same number, right? But what that tells me is the tool that I used in the second situation was so precise that it went all the way out to the 4th decimal place before the number changed. So it was like right on the money. So if I'm going to be doing calculations that have a need for more precision, I would want to use a tool that had more precision. So the significant figures are just a way to show how certain you are in your numbers. Very often you'll see this type of expression of plus or minus some value to tell you how off the tool is. But it's implied that if you were to write 88.00, that this number is your guesstimator, is the number that you're thinking about, you're estimating is that last digit. It's assumed. So if I were to say my measurement was, again, 12.0000, that would imply that I'm plus or minus 0.0001. So that it's somewhere between 12.0001 and 11.9999. I know that the number I measured was somewhere in between those two values. Pretty precise. Pretty precise. So the tool you use is going to give you a different degree of precision. Notice here I have two graduated cylinders. This graduated cylinder on the left measuring 8 mils. It's right on that line. And is it really on that line? I really can't tell, but it's pretty close. But I can tell on this one because it's a much smaller graduated cylinder that you're going to be a lot more likely to get a good measurement. So you want to make sure, again, this is one of these tricks we're going to use when we finally do get into class. Whenever measuring volume, try to measure in the top half of the graduated cylinder. You get a lot more precision that way. Okay, so what's a significant digit? A significant digit is all the digits in a measurement that you know of plus one, like we showed on previous examples, that you've estimated. How can we look at a number and determine the sig figs? Well, first off, anything that's not a zero is going to be significant. So 152 milliliters has 3 sig figs, and 2,594 kilograms has 4 sig figs, and 67 centimeters has 2 sig figs. So as a precursor, as an explanation as to why we're mentioning this, you do want to be able to determine the number of sig figs, and in this case, you're also going to have to know where the last sig fig is. So that 2 is the last one, that 4 is the last one, and that 7 is the last one, because you're also going to use that skill a little bit later. So the one is the last significant digit. Rule number 2, if you've got a 0 in between significant digits, it's going to be significant. So that 0 in the middle, it's not a zero, it's not a non-zero, it's a 0. But still, because it's in the middle, we are sure of that. The one we're not so sure about, the one we're estimating, is the 5. So all of those sig digits, the 1, the 2, the 0, we are all certain of, and the 5 is the one we're estimating. So that number has 4 sig figs. And 0.0086, that number has 5 sig figs. Okay, let's start talking about that 0. That 0 starts being in the beginning or the end, it starts getting crazy. Let's talk about in the beginning. If it's out front, it's not significant. So 0.00586 has only 3 sig figs. These zeros out front are not significant. Obviously, they're very important, especially the second two, because they give you a measurement of the magnitude of the number. You can't just drop them. 0.00586 is different than 0.586. But from a precision standpoint, if this happened to be in, say, grams, I could express this as being, let's see, 5.86 milligrams. I could just change the prefix, and now voila, I have a different number, apparent number of sig figs, but it's not. The tool that I use measures to the 100ths of the milligram. Okay, so that's got 3 sig figs. That number has 2 sig figs. It's kind of crazy, but sometimes old technology used to put the zeros out front. That's kind of weird. It's like saying, what's your grade in class? Well, I got a 0.98. Why'd you say the 0? That's weird. Okay, rule number 4. Now, we talked about the ones in the middle. We talked about the ones in the front. Now we'll talk about the ones on the end. And there's 2 separate rules, whether they're after the decimal or not. If they're after the decimal, they're significant. So these zeros are significant. These are bragging zeros. And this is the last significant digit. So this thing has 6 sig figs. That's telling you this is plus or minus 0.001. Really, really precise. This one has, that's the last sig fig, so that one has 5. Okay, and the last one is what if they're before the 0. Well, if they're before the 0, they're not significant. So I would just say 1,200. That's 1,200 plus or minus 100. So that's going to only have 2 sig figs. 6,870. Technically, since this is the last sig fig, that'd be plus or minus 10. So that has 3 sig figs. Now, what if I wanted to change this from having 1 sig fig to making it say 500 plus or minus 1? Well, I can't just change this 0 because it's a 0. Okay, but I can write this in a slightly different way. The correct way to do it is to change it into scientific notation. Change the number 500 to 5.00 times 10 to the second. Now this thing has 3 sig figs. So my answer, my sig figs of a number is there. And this does give the impression of plus or minus 1 milliliter. What's another way? Probably the most common way in our class, and you've already seen it because in the warm-up I used it, is to put a decimal at the end. It's kind of like saying, I'm putting this decimal here for a reason. I'm going to put it there for a reason. The reason is I want it to be good right up to that spot. So now this is my last sig fig. Boom. The last way to do it is a little trickier, and it's what if this isn't the one you want to have as your last one? What if this one is? Well, then, in order to make it plus or minus 10, I put a bar over top of it. Now my 0 with a bar over top of it is not the same as a 0. It's not a 0 anymore. It's called a 0 bar. And therefore, it's significant. Therefore, this has 2 significant digits. It's a way to actually change the number of sig figs in a number. Okay, so how are we going to use this? So to wrap this up with sig figs, let's wrap this up by talking about how you do the math. There's 2 different operations you would do in the class. One of my former colleagues used to always argue everything was just addition. And we can argue that one if you want, but it's just a matter of addition or subtraction. Reverse operations are one of it. Everything is just an addition. But we're going to look at the operation of addition and subtraction and the mathematical operations of multiplication and division. 2 most common ways you're going to manipulate numbers. If you are going to add or subtract numbers, what you want to do is make sure your result has as many decimal places as the measurement having the least number of decimal places. And what you're going to be doing is rounding to a location. The location, I use the fancy terminology, say, is the leftmost last sig fig. So I'm looking for the leftmost last. So when I line these guys up, if I do this math, I know that first thing I would do is just add these numbers up. There's what the calculator gave me. Then I would look at where's the last sig fig. There's my last sig fig. There's my last sig fig. And there's my last sig fig. So which one of those 3 is most towards the left? Well, the one that's most towards the left is the 2. So I now need to round this to that location. When I round it to that location, it gets rounded to be 22.1, 221.2 to the correct number of sig figs. Because this tool, the tool that was used to make this measurement, is only good to the 10th place, my answer can only be as good as that worst tool and be as good to the 10th place, no matter how great those other 2 tools were. Now, the multiply divide rule is a little easier to do, but also is sometimes mistakes are made. Multiply divide, what you're going to do is you're going to do your math, and then you're going to round your number to the whichever number of sig figs is least of all the numbers you're doing the multiplication and division on. So you're going to round to a number of digits. How many digits, how many significant digits does each number have? And then you're going to round to whichever is the smallest number of significant digits. So if I did this math, the 12.50 grams divided by 28.01348 grams per mole, then multiply times 22.4 liters per mole. This should look kind of familiar to some of you guys who in Chem 1 got this far. Then you do the math, you get this number, you're like, whoa, that's crazy. But I can't express my number to that precision, so I have to look at my tools. This one gave me 4 sig figs. This one gave me 1, 2, 3, 4, 5, 6, 7 sig figs. And this one, the number I use there, gave me 3. So the least number between 4, 7, and 3 is 3. So I need to round my final answer to 3 sig figs. Well, this number rounded to 3 sig figs would just simply be 10. Okay, you're rounding your answer to 3 significant digits. How many significant digits do you have? Not the location. How many digits do you have? Okay, so we're going to stop there, only because this has been a really, really long video. Hopefully a lot of this has been a bit of a review for you. I know that for a lot of you guys, sig figs was probably not your favorite thing to do in Chem 1, but it's kind of an essential component. I'm going to wrap this up by just saying try the problems that are a part of the homework. Do the best job you can. The owl sometimes is a little flaky when it comes to how it does sig things. Um, be patient. It is a computer, so sometimes it's a little more fallible than other times. And also, as far as this content goes, try what you can, but bring your questions to the synchronous time in class. Give us a chance to talk a little bit about where your challenges are. Until next time, have a great day. And I keep looking over there because that's where the video is in my face. Hopefully everything goes well, and I will see you next time. Toodles.